and today we're talking about safety and security. And the first speaker is Dr. Jan Oliver from Nokia Bell Labs. He's a distinguishable member of technical staff of Nokia Bell Labs, specializing on areas of trusted computing and safety critical systems. His talk is about cybersecurity and safety critical systems. In digital world that we live in the autonomous systems are very vulnerable in facing cyber attacks. What makes it worse is that attacks are very difficult to identify. Fortunately, safety and security technology exists to overcome these problems. The talk is dedicated to current state of combining security and safety in such systems through a Time medical case study. Dr. Oliver, the screen is now yours.
Okay, so good evening. I'm Ian Oliver from Nokia Bell Labs. I'm specializing in, well, as the title says, cybersecurity and safety critical systems. And what I intend to do in this talk over the next 20-30 minutes is just introduce you to the area and one of the case studies that we're working on and how trusted computing fits in with that particular case study. Okay, so we are seeing this mass digitalization of critical systems. I mean, it's already happened in aviation to a point, in industry to a point, but now with areas such as digital medicine, telemedicine, remote medicine, railways, etc., we're seeing the move from the classic mechanical systems into highly sophisticated, basically computing systems, from which are capable of not only collecting the data, but also responding to the events in those systems. The most interesting thing here is that these systems can now take advantage of very, very advanced data collection. We can move data to the cloud, we can perform analytics, we can do an enormous amount of work already on the device, and this requires significant amounts of software. It also significant amounts of firmware, sensors, IoT devices. You know, a typical medical device, such as a ventilator now, actually contains potentially 5, 10, 20 individual sensors, a number of microcontrollers, and can actually individually be made up of 5, 6, maybe even more individual computers all working together. So if you thought your PC was complex, even a small medical device is acting more like you know, a data center rather than a single machine. When you have all this, you are opening these devices up to a new series of attacks, new attack vectors. It's just natural that not only do people want to get the data off these things, but they would also like to get access to these things to make them do things they weren't designed to do, and so on. The update procedures for these devices can be very, very well, for a start, very necessary, but also remarkably simple. So there are medical devices such as ventilators out there. In order to update the software on them, it's literally just plug in a USB stick, and the software is transferred and the thing just runs. And the hardware that these things are running on isn't anything special. They are anything from typical ARM, Cortex, STM32 processors, small x86 systems. So they're no different from often your laptop or your PC at home in nature. So there's nothing really that esoteric about the systems that about the software that they're running. Where things have got very interesting over the past few years is the explosion in the use of microcontrollers and also PLC systems and connecting these to the internet. So on the right-hand side of the screen here, you see 3 very interesting examples. One is a Siemens PLC controller, this was the controller that was actually implicated in the Stuxnet attack, which is the canonical firmware attack that we all refer to, because that's the one that's most well known. This controller was collecting information from devices and controlling devices that was connected to an Iranian uranium reprocessing plant. Now, interestingly, the software update that caused all the problems there was actually designed not to destroy the system, but to cause mass inconvenience, to introduce errors and faults that were almost indistinguishable from mechanical failure. On the far right, this is the board of a common home medical device. it's still certified. It's a certified medical device. It's used for therapeutic usages. But actually on board is your typical flash memory. There's an STM32 microcontroller and a number of devices. The device actually runs a cut down version of Linux. There is over-the-air updates available to this. The reflashing pins are open. You can pull all the software off this device with a reflashing unit that you can buy for less than €100 from any reputable electronics store. And then you can take over this device. You have remote update mechanisms which are potentially open in this case. And at the bottom is a water sensor that that I found in a bathroom on the 7th floor of a building once. Nothing special about this. It's just a little sensor that detects if the bathroom has been flooded. It's a little ESP32 microcontroller, and you see the 6 pins of the reflashing pins actually exposed on the device. Now, while you think, what damage can you do by reflashing the software on a flood detection unit? Remember, it was exactly that kind of attack that has almost brought down a petrochemical plant in Saudi Arabia. It almost brought down the uranium processing plant. It's brought down power networks in Ukraine. And there's about 500-600 well-documented kinds of firmware attacks of the nature here. We also think of these systems in terms of their criticality and dynamicity. So trusted systems, which I'll talk about in a minute, tend to be very, very static. You like to know exactly how the system is being configured right from the start, and hopefully it doesn't change too much. On the other hand, dynamic systems, and the more dynamic a system is in terms of its mobility, the configuration changes, how various sets of devices come together or not, as that increases, it makes actually trusting the system more and more complex. So criticality on an exponential scale goes from home systems up through IT systems, automotive, rail, aviation, and eventually up to nuclear, who actually don't talk in terms of number of deaths, but in land area taken out of usage for the next 50,000 years. Medical systems, these are typically extremely dynamic in their nature, in that the amount of devices that can come and go at any point in time and the locality of those devices can be very, very very volatile, the configuration of the devices, to which networks they get connected to, and so on. So medical devices are proving a rather significant challenge for trusted systems. So while safety and security are two huge areas, we can talk about industry, aviation, and so on. The area that I've been working in for the past couple of years has been specifically on trusted computing and safety critical systems, so a much, much smaller area, and then specifically on medical and rail systems, which have particular constraints that make these systems, well, at least interesting from my point of view, although the basic techniques that we're developing here can be applied to all of these areas. And in the future, we're looking at aviation and drone systems in particular. So trusted computing is a concept that's been around for well over 20-25 years. The idea is that if you can prove or have some way of proving the integrity of the system that you're running software on, and then you keep on building that up higher and higher, then you can have trust in the system. And trust here doesn't mean that your system is secure. Trust means that you know what the system is. You know what it's going to do. You know how it's going to behave. You know how it's going to fail. And about 10 years ago, the Trusted Computing Group specified a device called the Trusted Platform Module version 2, which is a hardware security module. It's found on laptops, server systems, variations exist in phones, and so on, which, coupled with the ecosystem of software and the firmware on that device, can be used for a number of cryptographic functions, and also storing cryptographic measurements of what that system is running, typically gathered during the boot time and certain parts of the runtime of the system. Using this chip, we also get an identity of the system. We can pull off quotes or claims from the system, which basically tell us that I'm in this state. Here's the proof, the cryptographic proof of that, along with my identity. And I can pass this then to a remote attestation environment, which can verify whether these devices are not only who they say they are, but what they say they are as well. And if we integrate that with other services, such as the management operations of a system, such as the update mechanisms, SDN, and so on, then we can use this information then to ensure that the system reacts in a certain way under certain kinds of trust failure. It also gets particularly interesting that we can also integrate this with our supply chain processes. So we can actually have a cryptographic record of where devices are coming from. So there's a supply chain and provisioning process that needs to be very, very much explored. And this is going to become very, very critical, especially for devices in the medical domain in the future. If we have a TPM, then we can go through all sorts of interesting detection and measurement systems. I just noticed 2 diagrams here have got a little bit blurry, it doesn't really matter. We can take a number of boot time measurements from the firmware, the configuration of the system, the bootloader of the system. We have mechanisms like dynamic root of trust measurement, and certain instruction sets on certain CPUs, such as TXT on Intel, plus event logs, to give us a complete record of how a system has been booted up, how it's been configured, and what it's running. At runtime, we have other systems, for example, Linux IMA for doing static file system integrity. And then we have high-level components such as containers, etc., which are much more dynamic, but can be measured at least at load time, suspension time, reanimation time, and so on. And of course, then, as I said, we get into supply chain. Interestingly, the diagram on the far right, even though it's unreadable, but each of the boxes there corresponds to an executable that is run that configures your, in this case, laptop when it boots up. This is actually this is what happens in the 5-10 seconds between powering on the system and something like Windows or Linux loading. There's a huge amount of operations going on there, and it is completely open in many, many respects to tampering, and there's absolutely nothing you can do about it from the operating system level. So all your nice antivirus, not going to touch this layer, at least not in any easy way. Safety critical systems, when we get into these areas, bring in a whole new set of techniques. 2 I'm going to pull out in particular: root cause analysis and failure mode and effects analysis. Now, these are the base techniques, and there are much, much more secure techniques, or sophisticated techniques, I should say, out there for performing this. Failure mode and effects analysis is a way of going through a system as it's being built or as it's being designed and figuring out where in that system it might fail, what the severity, probability of this is, and how easy it would be to detect. The green table here actually shows a small failure mode and effects analysis for a single valve on an anesthetic machine. And it actually turns out that most of the time these devices are very, very reliable. They don't fail. When they do fail, they're kind of easy to detect, and they're easily repairable. You can get around them. Where it becomes very interesting is if you go and attack the microcontroller that's looking at these sensors, these errors become incredibly difficult to find, and they're incredibly destructive. So for example, if you have an anesthetic machine, if I wanted to really do some damage, I wouldn't stop the gas flow on it. I would actually go and alter some of the parameters on this, so the anesthetist actually gets to see correct results from an incorrectly working machine. Now, if that doesn't scare you yet, I have more coming later. When we've actually got a running system, when we do get failures, then it's often useful to go through a root cause analysis procedure. So if we get a failure, say a valve has failed on this machine, what's the procedure I need to go through in order to diagnose what really happened, what led to that? And often these are written in the language of the domain expert, not in the language of security. So we actually have very, very little in the way of root cause analysis procedures for dealing with security errors. And this is going to be more and more critical as we need to add security to these machines in the future. So the architecture of all this, I've talked about TPM. I mean, that's one small device that comes in typically as a piece of hardware. But what we want to do, and what my work has been now, is actually building this up higher and higher over the system. So how far can we go up the stack? Can we actually leverage this in the applications that we're building? Can we leverage this in diagnosing faults in the system? Can we leverage the information this device gives us in terms of the forensics? And I think part of the reason why this hasn't been done in any major way so far is because this has been typically on IT systems and single systems, or maybe server room systems. It's only now that we're actually starting to see these kinds of devices in very, very distributed, very heterogeneous, large-scale systems being deployed in safety critical situations. So the case study that we've been working on has been based around a remote hospital. So we have, say, some complex or critical medical procedure being able to be performed in a remote site, while the physician, the clinician who is an expert in that is at some other site. So full marks to anybody who gets the joke on this page. This is actually for a country like Finland, this is actually a very, very desirable situation. I mean, a large country, we have 5 or 6 main hospitals, but then we have a few hundred minor hospitals, and it's not always convenient to get a patient to a major hospital. So sometimes it's very, very necessary to perform some procedures remotely. And one thing that we cannot do at the moment is perform certain very critical procedures, such as remote anesthesia, which requires an anesthetist and specifically trained doctors to be actually present. But we do have various grades of trained staff, nurse anesthetists, and so on, who could probably take over on, shall we say, less critical cases. So this would actually enable some very if we have the security layer and then we have the trust and the bidirectional trust in the systems, then we can start to enable some more of these more critical case studies, safe in the knowledge that the system will actively defend itself from any kind of attack, and when it does go wrong, it responds in a sensible way that everybody can trust. So let's start off. I mean, what you see on the screen now is the user interface for an attestation server. And if you think this looks like the display panel that you might see on a medical device, you're absolutely correct. So we're now spending a lot of time to actually make security, and especially concepts like trusted computing, appear in the domain of the domain expert. I mean, as much as we say, people should know more about cybersecurity, know how to defend their systems and how to install antivirus, you cannot expect everybody to have the degree of knowledge that, say, a cybersecurity expert might have. That's impractical. It honestly doesn't make any sense. So let's start off with this. We have the remote doctor. He's looking at the status of his remote anesthetic machine at another site. And what he wants to know at this stage is this machine in the state I think it is? So we start off here. This is the base state. The next thing that he will do is basically just ask the machine, go perform your self-checks. Now, there are procedures for doing this in the medical domain. All we're doing here now is enhancing the medical procedures with cybersecurity procedures underneath. And this is a very, very simple test and response. So the machine will go and test itself. We might have a hierarchy of attestation service here, and that's another complex. But it'll go and attest the machine. What we see is some results coming back. Hopefully the doctor doesn't see this kind of display, and it's all reduced down to green ticks and red crosses. But we get the response back. We can apply rules over this to decide whether this machine is conforming to the necessary level of assurance. In this case, we get the result back and we see there are 2 crosses, red crosses. It says, look, there's a flow sensor and a pressure sensor that have failed for some reason. Now I know exactly why they failed, because I actually wrote the firmware for these myself, and I actually I deliberately put the wrong firmware on them. What this tells the domain expert now is that he's got a failure. There are a number of routes that you can go down. Now, what would happen in the medical domain is, first of all, you would probably start a detailed inspection of the sensor. Now, of course, once you have this kind of forensics, you've narrowed it down to some devices, you can actually guide the remote doctor to tell how his medical staff at the remote site, go check this sensor here, it's this one, it looks like this, etc. You're actually seeing there is a picture from the ventilator system that we built ourselves. It's not medical grade, but it would suffice in an emergency, I'm sure. The other thing that we can do is also check the expected data. So under failure here, you do not want to stop the operation of that machine. You want it to keep on collecting data. You still want it to work. And what we can do here is actually look at the data coming back. Now, there's a few very interesting things that we can do here. First of all, if we have a trusted computing base underneath, the data coming from that machine, we can run via the TPM. We can stream it through that with some suitable hardware. and actually sign that, not only sign the data that's coming off, but also enhance the data with the integrity measurements of that machine. So the data that we're actually getting on that screen there, now presented to the doctor, it says, okay, look, the patient is still breathing and all these values are perfectly fine. We can annotate that with marks saying, at this point, you can no longer be sure about the validity of this data. Then it's up to the clinician to make the choice. Well, this data looks absolutely fine and it's what I'm expecting, even though I can't trust it, which then would trigger other things such as going down the root cause analysis route to say, look, the data looks good, the sensor is wrong, and then the clinician can then be guided through which kind of response they want to make to that. So the upper part here is called Trusted Data Provenance. There was a lecture this morning given by myself. There's one yesterday given by a former colleague of mine. And there are a number of papers on this that I can give links to later. So the question we now want to ask is this a physical failure, broken valve, patient physiology, or is this a device trust failure, i.e. the firmware or the configuration change of the system? Now, in this case, what has actually happened when we do this, we either change the firmware on the system or we actually change the physical device. Now, you can imagine the doctor now over the video link back to the nurse saying, can you go check this sensor? How is it? Was anything changed? And then the response comes back from the human response saying, yes, maybe we changed the sensor this morning, or we uploaded this software to it this morning, and so on. And therefore, the attestation can be changed around that. In order to do this, we require from the trusted computing start quotes, PCRs, and event logs. So the quote is the claim from the machine that it is in a certain state and it is the machine it says it is. The PCRs give us the next level of information, the next level of forensics. These then can tell us which parts of the system have actually been tampered with, whether it's configuration and so on. You can do this exactly the same with your laptop during its boot process if you enable the TPM on board. And then if necessary, we can go down into much more detailed event logs and audit logs that these systems have to produce to go and find out precisely where the error is happening. Now, of course, all this should be automated. And indeed, we have built an analytics system based upon one Nokia product and also upon the Elasticsearch Kibana stack on top of that with various rule systems. So we do have, if you like, an AI ML system that can go and actually understand these and then drive a root cause analysis. The root cause analysis now, as I said before, these are very complex trees. What we can do now is sort of aim into one of these trees based on these forensics. It must be this kind of error. And as we dig down that tree, then each point in this root cause analysis tree might then trigger further forensic analysis, either from the device itself or from the logs already gathered, to tailor precisely what fault has actually happened. And this is going to be critical as we move to more and more remote systems. We are going to be in the state where we need much more assistance, and especially if we bring in the cybersecurity aspect to help the domain experts actually figure out what is actually going wrong with their systems. Finally, we want some kind of automated response. Now, in the case of, say, a remote medical system, the automated response would be to try and patch the machine as much as possible, or try and figure out where the machine is outside of its known parameters and so on. In other systems, it might go and direct maintenance team to go in. It might also trigger automatic updates of the system in order to get back into the good state. In the case here, when we run this demo live, actually we show the automated response, and as you can see on the right-hand side, now all the boxes are green apart from one yellow triangle for demonstration purposes. So the conclusions of all this is that trusted computing, as well as providing the device and device integrity, so we can have trust in the devices. I remember it is just as important to know that your device is in the wrong state as it is to have the correct device, because at least you know it's in the wrong state, which is a very critical thing in lots and lots of systems. It also gives us the forensics under those failure conditions. And that's critical for safety critical systems when we want to try and diagnose what's wrong and actually come up with some basis for levels of assurance in the system and how we construct the automated response to those failures and keep whoever is connected to those systems in a safe state. Automation of this is actually exceptionally complex, it turns out. The event collection is the first part. How do we get these events? We need to build this infrastructure. And what we're actually doing now is starting to integrate quite a lot of this infrastructure into the, should we say, the upper layers or the security layers of the 5G networks. How we orchestrate around that and how quick we do the response, what's the latency. If we get into the rail domain, the latencies come down dramatically from the medical domain. We need better mode analysis of the systems. And mode analysis here says, okay, how do I know when the system is moving between its known state or its good state and its failure states or different kinds of failure states? How do I recover from that? How does the functionality of the system degrade as we lose trust in the system or as the integrity fails in the system? And degraded functionality is one of the keystones of safety critical systems. So for example, rather, best well known from aviation, if an aircraft suffers a failure in flight, and this actually happens quite common, the aircraft will actually return partial control or more control back to the pilots. So there's always a human in the loop to take care of these failures and actually understand what's happening. Mitigation of these is actually unclear in many systems. So in a lot of medical systems, railway systems, cybersecurity is completely new. We just do not know how these systems should react under failure conditions. And that's going to be a big learning for us. And this, of course, then has an effect upon the learning and AI algorithms that we invariably have to build as the complexities also increase. I should also point out, while we've talked about RCA trees and failure mode effector analysis, there still is no real good mechanism for merging these together. So while we might have a root cause analysis mechanism for, say, anesthetic machines or any other medical devices, and then we have one for cybersecurity, these two individual trees do not mesh very well. So you're getting some very interesting orthogonal yet linked responses that we don't properly understand, and we will not probably understand them until we start building more of these systems and then properly attacking them, and which is effectively what my research is about at the moment. Like I said, the other case that we're also going into then is the railway domain. We're hoping, well, we do have a simulation of this running. We've got a much more extensive simulation where we can replay further attacks against this. And we have a simulation of the Finnish railway system, or at least partial part of it, where we can tamper with devices, replay these back against real signalers against the system, and let's see if they can diagnose the system. And from that, actually discover how we build root cause analysis in with both the domain expert and with the cybersecurity taken in, and how this actually affects in real life. So we have the railway simulation being built now. We will have the first medical simulations early next year with a bit of luck as well. So in conclusion to this, what I'll say is, as our safety critical systems, medical, rail, aviation, automotive, etc., become more and more digitalized, we have to add security into these systems. The only problem is that introducing security into these systems is now going to introduce many more new and actually novel failure modes into these systems that are completely unexpected. So protecting your system will actually give us a whole new set of ways in which these systems are going to fail. And what we hope at the end of the day is when they do fail, is they'll fail in a way that means that we are still protected and that we are still safe. Therefore, safety critical systems living up to the name as being with the word safety in there. Okay, I will stop there and I will take questions. Thank you.
Thank you very much, Jan, for a great presentation and the knowledge that you shared with us.